Before we start, who of you already knows what TDD is or has been in Phil Nash's great talk right now? Okay, all of you. That's great. I assumed so much. Who of you is working on microcontroller? Okay, about a third. Great. So all the rest of you will get an impression what the difficulties in embedded really are. The ones who already worked on microcontroller maybe get a few new ideas how to apply TDD. But first, maybe a little bit of background. So I used to be an embedded software engineer. I worked in safety-critical systems. So when I got there, I assumed there would be a lot of testing there. I mean, even before I was an engineer working in traditional software, like server backends and desktop programming. And even like 15 years ago, it was pretty common to do unit testing in this traditional software development. Some people even did test-driven development. So when I first came to embedded, I was astonished that unit testing is not really used that much, and TDD was basically unheard of. And I think this is still the current situation. I mean, more and more people use unit testing, but TDD is mostly not used in deeply embedded projects. So in this talk, I will want to give an overview what the obstacles are if we can use TDD, and present the state of the art and give a few ideas how we can improve from there. So this will not be a talk about TDD itself. We just saw all of you are basically familiar with TDD. So what's important for this talk is this TDD microcycle. First, write a test, have a failing test because there's no implementation yet. Then you get the implementation right, and you get to this green part. And then really the magic kicks in because you have the safety net. If you developed all the parts of your application, of your program with TDD, you can freely refactor, change things, and you fall back to your tests, and you know you don't break anything. This is really, for the sake of this talk, the most important benefit of TDD. And this requires, and this is really the heart, a quick and automated feedback loop. Feedback in this sense, you try something, and you get feedback if it's working as intended. TDD was made popular by Kent Beck. So all of you who want to read a good book, Test-Driven Development, it's still relevant. It's from 2002, but it gets the basics really good. So I highly recommend it. So what's different in embedded than in traditional software? In traditional software, when you want to try it, when you want to get feedback, you run the program. In the most simple situations, you just click on the binary, run it, click through the application, and get to the part you want to test. It's a manual test, but you can just do it. In embedded, it's totally different. To test something in embedded, you need to get the microcontroller, get the hardware. You need to flash your binary on the hardware, and then you need to execute it there. And you cannot click through it in most cases. You need to use maybe sensors, maybe send some data to it to get it in the relevant parts of the code. So this process is much more manual and time-consuming. Yet this way here of trying code is really like the standard. A lot of people working on deeply embedded stuff do exactly that. So in traditional desktop programming or traditional programming, we got unit testing to test isolated parts of the code. And this is really the core of TDD, write good unit tests. And the key of unit tests is that they focus on some parts of the code and basically can ignore the rest. You abstract away all dependencies, and then you can focus on a single part. This means, for example, if your application has a dependency on a database, you abstract away the database, insert a mock or something, and then you test against this abstraction. And you can focus on your code. And the question here is, can we do this in embedded? Abstract away all the code we don't need and focus on the parts we are interested in. can we use things like unit testing in embedded. And in 2011, there was a really groundbreaking book on it, Test-Driven Development for Embedded C from James Grenning. Who read this? Okay, only a few people. I can highly recommend this one as well. It's fully applicable to embedded C++ as well. It deals with how unit testing can be applied to the embedded world. And the important principle he established is so-called dual target testing. And we will first now focus on dual target testing. So basically, I will explain the most important concepts from the book, and then we will see what is still missing and how we can proceed from there. So dual target testing means you run your unit tests in different ways. On-target testing, the part on the left, means you run your tests, your unit tests, on the microcontroller. So target means microcontroller in this sense. So to do this, you need to develop code and tests. You do this on your host, or your desktop machine. Then you cross-compile it. So you use embedded compiler like ARM-GCC or Kyle. You have a binary, and you can flash this binary to the target and run the test there. And of course, you need some way to view the results on the host. This is called on-target testing. You test on the microcontroller. And it's kind of slow because you have this hardware dependency, and it's a little bit difficult to automate. So James Grenning proposed a second way. He called it off-target testing. And in off-target testing, you execute the test on your machine. So you don't cross-compile, you compile with your standard GCC. You run your tests on your PC, and you view the results there. This is obviously much faster. You can even run it on the CI. So what kind of code can we test with off-target testing? And what kind of code do we need on-target testing for? Let's first start with off-target testing. To do off-target testing, you need to compile your code with your desktop compiler. I brought a function here, CSC32. It's basically calculating a checksum and returning this. So the inputs, the implementation is not really important. The inputs are a range of bytes, and the output is a 32-bit value. So this stuff is supposed to run on a Cortex M33, so an ARM Cortex controller. Can you just take this code and test it off target on your machine? Okay, why not? Exactly. We can't. This header here probably won't be available on our desktop machine. Yeah, usually a lot of these headers are just shipped with the toolchain, so they belong to the compiler, and they won't be available here or on our PC. Fortunately, if you take a detailed look at the function, this header in this case is only used for some custom 32-bit definitions. And that means we can decouple this code. We can say, oh, since C++11, we have this standard header stdint, and a 32-bit value is in the standard. So the code can be generalized to make use of the standard header. And now it will behave the same on the target, but we can also run it on our PC. And this is great, because off-target testing is the fastest way to develop and test code. So we can write a unit test like this. Give it some sample data, run the function on it, and compare it to some magic value we get from some example, or maybe there are website generators for CSC. We can get it somewhere. And then we know the implementation works. You can screw up a lot of things in CSC calculation. It looks simple, but there are so many parameters you easily screw up. Okay. If there are any questions, by the way, please feel free to just raise a hand and interrupt me. I think we have enough time today for that. So what is off-target testing? What do you need to establish it? You need a certain setup. And for most embedded projects who don't use this yet, that's a new thing. They need to set up a different tool chain. Yeah, your primary tool chain is your embedded compiler, like Kyle. You need to add another tool chain, like a Clang or Microsoft Visual Studio Code, or GCC, or anything else for your host. So if you use CMake, for example, you can use these .toolchain files to give it another toolchain. And then you need to compile parts of the code that you want to run off target. And of course, you need to integrate a unit test framework for that. The good thing is here, you are off target on your PC. You have basically unlimited resources. So you can pick any recent unit test framework, like, for example, Catch2. And then, and this is really the critical stuff for embedded projects, you need to make sure to decouple the relevant code from all hardware dependencies. It's really easy to get a hardware dependency when you program for embedded microcontroller. Yeah, maybe in some included nested header is some definition that won't work on your PC. This is really the critical part, decouple, especially for legacy projects. Okay, but then we can run this code, and we can have a quick TDD feedback loop. So all the requirements are fulfilled. We have automated feedback, and it's really quick. Great, so why we don't use off-target testing for anything? There are two important limitations. And the first one is there are risks. And unfortunately, even in safety-critical systems, a lot of people are not aware of these risks. So I brought a slide here with a little code snippet. What you see are two functions. And function 1, function 2, they are just printing out their name and returning an int. And there's a third function, foo, taking two int arguments and also printing its name. And in the main function, you just call foo with the return values of our two functions. And if you execute this on your desktop machine, off target, you get a different result than on target. For example, on the Cortex M4, so ARM Cortex. Anybody knows why this is in this case? Yeah.
Order of evaluation of the arguments to foo.
Exactly, and this order of evaluation is unspecified. The standard says this is up to the compiler implementation, basically. So, yeah, the C++ standard just says the order of evaluation of arguments is unspecified. Okay, and this is a definition of unspecified behavior. It depends on its implementation. So the compiler writer can basically decide which implementation he chooses. And of course, this can make a difference in program behavior. It's pretty obvious. So off-target test would have a different effect than on-target. There are much more risks. I won't go into details. There are other language-specific things. Hardware problems. Your hardware can have defects. You can have bugs in the toolchain. If you look up how many open bugs there are in ARM GCC, you get really nervous. And they are losing. Yeah? Each week, more bugs are introduced than solved. Most of this is rather, you would hit these behaviors rather seldom. But seriously, if you do unit tests and you have an option to catch these things that will take you days and weeks in production to find, why not use it? So for these risks, to mitigate them, you need to run your off-target tests also on the microcontroller, on target. Only then you test the object code that will really end up in production. There's a second, more fundamental problem, and this is hardware-dependent code. So your CSC function could use some hardware functions from your microcontroller. So for example, all these examples will be based on an STM32 microcontroller. And this controller has special function registers, hardware periphery, for CSC calculation. So you see this code really writes to this special function register here and returns some value of it. And obviously, you cannot compile this code for your PC. Your PC doesn't have these registers, it just won't compile. And the question now is, I would like to write a unit test like before. Can I do this? Test this hardware-dependent code. And the answer is, of course, you just need to establish on-target testing. And this means you have to take your code base and, again, integrate a test framework. If you use an embedded compiler, these compilers, for all of you who are not working regularly in embedded, projects often have to use really old compilers for different reasons. And these compilers don't support the latest C++ feature, so sometimes you cannot use the modern libraries. Then you need to use maybe a C testing library like Unity or CPPU test, but you will find a unit test framework that compiles also with your ancient cross-compiler. So choose a unit test framework, and then you adapt it so it compiles for your target and somehow outputs the results. Maybe stream the results to the UART, to the serial line, and this you can catch on the PC and display. So this is in principle pretty straightforward. You can have automated feedback. Yeah, you need a setup. You can do it. And this feedback can be quick. The bottleneck is usually the flashing of the microcontroller. But for many microcontrollers, you can get down to like 2 or 3 seconds with decent tooling. So it's possible to use TDD for this hardware-dependent code. That's really important. There are no things preventing you from using TDD. You can have this quick feedback loop. Which brings us to the, I would call it, state-of-the-art in testing, and this is pin behavior. I mean, we are talking about embedded systems, and they are called embedded because they are embedded in some environment, and their primary purpose is to interact with the environment. Maybe measure some value with a sensor, maybe control a motor, interact. And this interaction happens through the microcontroller pins, and only through the pins. So a lot of deeply embedded code is about getting the chips to do the right on the pin level. How can we test this behavior? I mean, how can we test this piece of code here? It's the purpose is to send 4 bytes on the UART. And it's using the HAL library from ST. It's called CubeMX. So basically, within these yellow function here, the code will do a lot of accesses to special function registers to the periphery of the pin to get these signals on the line. And what we want to know is, if we write this code here, will this happen on the line? That's a logic analyzer attached to the pin, showing us the result. And unfortunately, that's state of the art. You program it, and you look at the pins. And this is really cumbersome, because you need special setup. You need to access the pins, maybe you need to solder to access them, you need special equipment, like at least a logic analyzer, but if you want to send data, you need a serial probe. If you're working on CAN, you need a CAN dongle, all kind of periphery. And if you need it, you don't have it, or it's used by some colleague, it's really a hassle. It's really a hassle. So what can we do? How to test this? Manual-based testing, I just told you that, and it's really the common way. There's an alternative, register-based testing. And I would call it industry standard, but I think it's deeply flawed, at least in the context of TDD. So let me elaborate a little bit. The idea is that we don't need to look at the pins. The core idea is, hey, we have a specification. We have our reference manual. For all of you who don't know, this is a very long PDF, very long, like a few thousand pages, filled with detailed information. On each page, there's potentially important information. It's crazily dense, yeah? But it specifies what happens if you write certain values to the registers. And the theoretical idea here is, okay, we use that. We rely on this specification, and if we do what is written in the specification, everything will work. I don't need to test it. Yeah, so what does it mean here? Let's say you are initializing the UART here. And inside this function, there will be a part of the code that's setting the baud rate, the speed at which signals should be transmitted. So it should be 115.2 kilobit. That's our goal. So let's write a test for this using register-based testing. Let's execute this code up to the init, and then we just assert against a specific register. We look up the reference manual. There is a baud rate register. That sounds great. So let's assert against the content of this register. The init function should set it. So let's just test it. OK, how do we get this value? And now it gets to real fun. I mean, Phil talked about the dopamine. You won't get dopamine there. I will tell you that. So first, you need to locate the chapter. For this STM32, the UART is in chapter 57. That gives you an impression already. You briefly look up how long it is. OK, only 86 pages. That's OK. You look up this register. Great, you found the essential part. And it actually doesn't tell you anything about the speed. It tells you, I know this is a little small in the back, but the contents here are not so important. So it basically tells you what bits you need to write to access a value called USART diff. OK, that doesn't. You need to look it up in the manual, and then you find an equation. And that's good. The baud rate is some clock, I presume, divided by the divider, by this USART diff. OK, great. But what's the clock? You go further, and it's getting smaller, yeah? You find the clock here, and it's divided again by some prescaler and another clock. That's all in the UART chapter, so pretty easy, 86 pages. But the clock here, this USART clock, it's described in a totally different chapter about the clock tree. And this is really the relationship here. On the left is your input clocks, like an external oscillator. And then there are a huge number of configurations, and then there is this clock coming out. So, yeah, you need to know all these values to calculate the magic value for BRR, to be sure that it's 115.2 kilobit. And I think you would agree this is not fun, but OK, maybe we can do it. But there is a fundamental second problem. So the first problem was it's just complex to find out the correct values. And it's not, the problem is not so much the UART itself, but the interconnections between different peripherals. If you need to think about UART, you will also configure the clock tree, OK? But you also need to configure the pins that, for example, this GPIO pin switches to UART functionality and really prints out the UART stuff. So there are multiple components interacting with each other. So this is difficult to find the correct register values. The second thing is much more problematic, especially for TDD. It's a white box test. You test against a specific implementation. Because what you did here is basically the same you would do when you implement it. And white box tests don't fit into TDD. Because in TDD, you want this refactoring to work. Make changes to the code base and be sure that your tests catch if the functionality changes. Let's say you change the prescaler and the baud rate registers, both by a factor of 2. This will cancel each other out. The baud rate is the same. But the registers look totally different, so your test will fail. So this is a fundamental problem in register-based testing. So, sorry. we need to find a way to involve pin behavior, to really test what is happening at the pins and not some thoughts about or assumptions about our implementation. Test at the pin. This is what will drive success or failure in the production as well. So what I will now tell you is something we at my company call open loop tests. It's a new way of testing code that is hardware related and make changes at the pin level. So open loop testing makes 3 requirements. First, you need to have your pins accessible. So you want to test on the pin level of the controller, so you need to have it accessible. Second, you have your code accessible, so that you can call single functions in the code and see what they are doing. And the third and most important one is you have to make your periphery accessible, so that you can, for example, write a test that sends a can frame on the pins, so that you have a test system that can be configured, that you can send frames on the pin level, or send SPI comments, or I2C, or all the other hardware periphery stuff. There are a lot of protocols out there, but on the pin level, not in some simulation. So the following slides, they are examples based on our execution platform. This is our first commercial test system for open loop testing, but the principles I show you apply to everything else. You can, with the principles I tell you, you can basically set up your own open loop test system. So what you can do when you have this kind of test system, so the test system here, this is important, integrates your specific microcontroller. There are hundreds and thousands of different microcontrollers. So the microcontroller will be plugged into the test system. For our thing, these little PCBs look like this. So small PCBs with a connector, and all the pins are on the connector, and the chip is basically here. And then, with this principle in place, you can write tests. The tests for our system are written in Robot framework. It's an open source framework, really good framework for all kinds of automation. If you go into this direction, take a look at Robot framework. Highly recommend it. And all the functionality and the periphery is available here as keywords. But yeah, we have enough time. I will make a brief demo. Let me switch here. Okay. Is it readable in the? I can increase the size a little bit. Yeah, it's okay? Great. So what I'm showing you here is an online version of Visual Studio Code. And this Visual Studio Code is connected to one of our test systems. So we have physical hardware, and we will test this SDM chip I mentioned earlier. So what I want to show you is a UART test. So let's say we want to check that our device under test, DUT, is receiving UART data. We send data to it on a pin, and we want to test that this data is actually processed and is arriving there. So on the C++ side, we have this function here. In the main function, we initialize the UART. Basically, this is copied from the CubeMX from ST. Pins are initialized, clocks are initialized, and then we have here, this is important, the definitions about baud rate. We want to send 8 bits. We want to have 1 stop bit, no parity, and then we start it. And it starts receiving here. So this is the implementation on our microcontroller. And we want to test that it's actually receiving data. And for this, we register a certain function. We write a helper function. It's called showReceived. It's over here. It basically looks at the UART looks if there are characters that were already received and prints them. Now with std out. That's it. No magic here in this function. That's important stuff. Make this function available. After this register, the test system can call this function. Remember, it's for open loop tests, it's required that you can call functions on the chip. And then just messages from the test systems are processed. So let's go to the test sequence here. The test sequence, as I said, robot framework, does a suit setup. This is executed one time at startup. And this suit setup flashes the firmware. So it takes the result from the CPP, the binary, flashes it on the microcontroller. And then we call this endpoint the interface to a specific periphery, in this case UART. Our test system is configured to have a UART on these two pins the microcontroller is also using. We initialize it with the bit rate, no parity, 1 stop bit, and 8 data bits. Of course, the same configuration we use for the target. And that's it. We can write a test now. Test that a single byte is received by the DOT, or the microcontroller. It's the same here. So for this, we will use the test system endpoint to transmit data. So let's just transmit hex data of maybe 6B. And now the system will send this data on the pin, and we need to read it from the microcontroller. So we will use dot invoke. This lets us invoke any function that registers on the target. I think it was called show received. Yep, show received. And then we need to get the output that's written to std output. We save it in a variable. This is now a syntax from robot framework, not so important. And then we can do our assert. Like in a unit test, we can say should be equal. And we take the first line of our output. And now we need to compare it against the output of the show received function. So Rx hex, and then the actual value should be 6B. Okay. I click on compile here, and then I run the test. So now this firmware is flashed on physical hardware, and on a physical pin, the data is transmitted, and it passes. Great, let's just copy-paste this and make a few more bytes. Test that multiple bytes are received. Let's use 7C, X8D, X9E. And then we need, of course, to change the expectation, 8D, 9E. Let's run this test as well. It's passing as well. And what's important here, what I want to show you, is the speed of the feedback. Yeah, I run the test, or the suit, both tests, and within seconds, I know that the implementation is working on the hardware. No manual steps here. And to show you that this is really running in hardware, I'm opening the logic analyzer. This demo system here is connected to a SALI-I. It's a logic analyzer. And the test system can be configured to output arbitrary data to the logic analyzer. So we will, we see the receive and transmit line here. So let's start capturing, just to see if there's really something happening on the physical lines, and we are not living in a simulation. I'm running the second test. Capturing stop, this is great. I need to zoom out a little bit. Yeah. So here's data on the receive line of the UART, and these are the 3 bytes we really wanted to send. So you can always check that this is really happening on the pin level. and you can compare arbitrary signals. This is great for debugging. I mean, Phil mentioned it earlier. TDD is about writing tests, but in some situations you just need to debug and look at the pin level. Okay, so that's a feedback loop, but let's use this. I mean, we have tests in place. Let's change our implementation now. Let's say you have noise on your line and you want to use parity. Parity is just a mechanism that in the UART data, one bit is calculated with a checksum. Yeah? And this is done in hardware. So we use odd parity. We don't change anything else. We recompile. And the only thing we need to change in our test is the configuration of our endpoint. We need to match it, of course. So let's have odd. And then let's assume you do this on your desk. Maybe you run a single test then. You run this first test that's sending a byte. And the test passes. Awesome. Seems to work. We ship it to production. No, please not. Let's run both tests because an error was introduced here. I think it's you won't be able to read it, but it tells that it's not received. It should have received 7C 8D 9E. Instead, it received 7C 0D 1E. And this is one of the situations where an embedded developer pretty easily spots the mistake, like Kevlin said, with his special date values and so on. It looks like the 8th bit, the most significant bit, is set to 0 for some reason. So obviously, our change didn't work. And for most setups, this would have been catched only in production later. Yeah? But we want to do test-driven development. So we can take a look in the implementation again. We set the parity. And maybe we are lucky and the ST documentation tells us what the parity is doing. And yeah, it says when parity is enabled, the computed parity is inserted at the MSB position of the transmitted data. 9-bit when the word length is set to 9 data bits, 8-bit when the word length is set to 8 data bits. So they have a pretty specific understanding of data bits. They basically say, yeah, data bits is not just data bits, but also parity. So they overwrite the data bit here. Fortunately, you can just set it to 9, to the word length of 9, and then we have the behavior we would expect from other implementations. So we recompile it, and again, we use the tests. And now everything passes. And this is really only possible if you have automated tests. In the case of the execution platform, that's how our system is called, there's really everything automated. So you need to wire anything, you can attach all the pins at runtime, basically. This demo is, by the way, public, so I will later have a slide with a link. If you want to play it, it's free and public. You can experiment for yourself. So let's go back to the presentation. Nope. Second. Yeah, okay, great. So that was a demo. That was the example I just told you. And now a little bit summary for open loop testing. So the important part is really the setup. To do this in your projects, you need to make the pins accessible, the code accessible. You need a way to talk to your code running on the chip and make the periphery accessible. So if you need UART, you need some UART dongle. If you need a CAN dongle, and then need to be all scripted and automated. Then you can build such a solution up. And then for each test, you write the code, compile it for your target, and you write this test and run it on your desktop machine. The robot code is running on the desktop machine. And then we really have a way to use TDD even for code that's changing the behavior on the pins. We get quick feedback, it's automated, a few seconds if you do the setup right, but even if it's 10 seconds, it doesn't really matter. The important thing is you have automated feedback. And that's it basically. On just a summary and maybe talk a few seconds about scope. So we saw off-target testing. You can run all your generalized code on off-target testing. All the code that's compiling on the PC as well. Be aware that there are risks. So if possible, in any way, run the same tests also on target. You need setup for this, but then you have all the benefits and mitigate these risks. On-target testing can be used to test internal periphery. So, for example, the crypto unit, CRC, flash writing, all this kind. You only need on-target testing. And the third thing is open-loop testing, what we call open-loop. And for this, you need special equipment, but you can test basically everything the microcontroller does with the registers. Because the pin level is the most important interface of the chip. We should be able to test it. There are a few references on the left. I really recommend this book here by James Grenning. It's from 2011, but highly relevant. Okay, that's it. Thanks for listening. Of course, I'm ready for questions.
Hi, thanks for the talk. So my question would be, like this on-target tests look more like integration tests when we comparing to traditional this unit integration test separation. So like let's say in your projects, what part of how much of the tests belong to on-target tests and how much to off-target tests?
So basically all the off-target tests should be run on target as well. So the coverage from everything you can run off target, you can also run on target. And you should use that. It's really a runtime setup. And it really depends what kind of project you're working on. Most projects we are involved are like industry scale projects, maybe different microcontrollers, and they are running for the projects running for multiple years. So all these projects can, and they do, make an investment in the test equipment upfront. So they use all the testing also on target. If I wouldn't have this setup, you really need to think a little bit strategically what kind of parts of the code are really the most important and focus on that ones. I mean, if you don't want to use on-target testing, you can also say, I'm using sanitizers and code checking and everything and rely on that. But in the end, these are all tools that also cost money and effort to maintain. So I would really always introduce on-target testing for serious projects. And maybe it's a bonus slide because you mentioned integration testing. And yeah, that's really it's a discussion. Yeah, what are we doing here? So traditional unit testing is called like component testing. Yeah, and this test pyramid, the lowest level. And if you do open loop test, if you do on-target testing, I would say you are still doing unit testing, just in a different environment, because the concepts are really the same for on-target testing, not for open loop. Open loop is a little bit more up. So from this perspective, what you do in open loop testing is basically replace, you use mocks for the external interaction. That's what it really is. So it's a mix between unit testing And in some norms, it's called hardware-software integration testing. So this level here. No. Did this answer your question? Good.
Hi, I was wondering, because I'm a bit familiar with Rover framework, and I know that it's quite the pile of Python beneath.
Yes.
How do you guys handle like even mild real-time requirements? Like, let's say I don't know, switch debouncing routine to take something really simple. How do you handle like even the possibility to toggle the pins randomly fast enough?
Yeah, that's a good question. So everything that's running in robot is not hard real-time. So you have basically no definition how long these commands will execute. They're running on your PC. So everything that is time critical is moved inside our test system. So in the system, there is an FPGA handling all the real-time requirements. And for everything that really needs real-time, you call specific keywords. For example, for this toggling example, you have a keyword that sets a pin for like an arbitrary amount of time. And you can run pulses with like 100 nanoseconds or so, because the test system is handling and not robot framework.
Is emulating also, would this work, emulating the hardware instead of running it actually on the hardware?
Yeah, that's a really good question, and there's a lot of debate about it. But so people tried this, emulating the chips. And for the simpler chips, like from 25 years ago, this kind of worked. No? And they don't do it anymore, because they just noticed the model of the periphery to get it done in simulation is just too complex, and we have too many faults in our simulation that it's really usable. So, for example, ARM, they recently offered, they call it virtual hardware. So basically hardware in the cloud. And they are modeling everything up until the pins. So they model their cores. They are Cortex M3 core, M4, all these cores. They basically own the IP, and they put a lot of effort into it to make really good models. And this is working. But from this level on, there are just too many peripheries out there. There are certain microcontrollers that offer this, but it's really hugely expensive. And you always have the danger that the actual model is not really using. I mean, to know that this is a problematic approach, look at the errata. Like, make up the errata basically says what's wrong in hardware. Yeah, and you find a detailed list, like 10 pages or so, from really intricate things that they did wrong in hardware. And they make a lot of tests before they put this hardware into silicon. So it's really difficult, and I would always recommend to really run on hardware.
I have a question. Is it on?
I think so, yeah.
Yeah, so I have a question. You said you had some experience regarding functional safety. Do you already have some experience how much the TÜV likes your tests?
No, not yet. So what I do know is there are different approaches basically to testing or to assuming functional safety. There are this black channel and white channel definitions, and from what I hear, so our system was not yet used for certification, so I cannot speak to it. From what I hear, they really the norms are sometimes requiring it, for example in automotive, but they try to get around this pin level testing, really. What they do a lot is like this register-based testing. It's really a thing even in functional safety. And I don't know of any examples that use this test level, like this mix between unit and hardware-software integration testing for certification. If anybody knows an example, we should talk later. Yeah.
A question to a test approach that we've seen lately and grow fond of. What do you think about basically unit testing, what you can test without hardware interaction, and leave the rest to integration tests?
So the question here is first, what is integration testing? I mean, I know a lot of projects that do unit testing and then system testing. That's like in industry projects, they have a department for testing and they do system testing. And what department is running the integration tests in this case, in your example?
It would be the system test department then.
The system test, okay.
Yeah.
So, yeah, it's a way to do it. What you need to consider is the feedback time. Yeah? So if basically in these situations, the developer does something and throws the code over a fence and then different department is acting on it and you have like a few days, maybe weeks, maybe months, feedback time, and this is not suitable for TDD. But yeah, I mean, if you have these tests, that's a good starting point, yeah? A lot of projects don't have these tests at all.
Maybe a follow-up question. How many bugs did you find in the low-level pin tests? I mean, for this to kind of trigger, you would have to have issues in either your configuration or in the final hardware, right?
So most of our customers, I mean, we are selling the test system. We are not, so I cannot give you precise statistics. But most of our customers, they are like projects, they write their own hardware abstraction layer, their own drivers, because they just see on the market there are different microcontrollers, and they have a lot of projects, but they want to reuse code, make platform-based development. So they take the cheapest microcontrollers for each project. But they want to reuse code, so they need the same hardware abstraction layer. So basically, they start re-implementing all this code that is, that you see in the, for example, the hull from ST. I mean, if you start implementing the hull, these functions here, you have a lot of work. And then it's not just configuration, but really testing your specific requirements. Against different families, yeah? Maybe one is an ARM and one is something entirely else, a tricore or something. Yeah? So it's not about configuration, it's also about configuration, but if you really use to reap the benefits of this is when you also do the driver programming.
Any others? No? Nothing online. Okay, I think we are done. Thanks again, Daniel.
Thanks for listening.